Hello, welcome to Maths with EJD. In this video, we'll be talking about Laplace transform for Dirac delta function. So, of course, before we take the Laplace of any function, we need to know what that function is about. The Dirac delta function. In the previous video, we had considered the Laplace transform of a unit step function. Now, we're talking about Dirac delta function. So the Dirac delta function denoted as delta t, delta of t rather, is a mathematical concept introduced by physicist Paul Dirac, primarily used to model impulse-like phenomena. The other case we considered was for functions that get switched on at certain points, but here we are talking about impulse. Primarily used to model impulse-like phenomena such as point sources or forces in engineering and physics. Okay, so the Dirac delta function is not a traditional function. I mean, the regular functions we know, right? It's not a traditional function, but a generalized function. It's a generalized function, or what we call a distribution, or a distribution. So we have a lot of this in statistics and probability, and and is formally defined by its shifting property. So the other time we talked about shifting, now we're talking about shifting. It's defined by its shifting property. And that is that integral from minus infinity to infinity of f of t delta t minus f of t multiplied by delta t minus a dt would just simply give us f of a, basically. So, and that happens for any continuous function, f of t. So this property, this property implies that the Dirac delta picks out the value of f of t, picks out the value of f of t at the point where t is equal to a. See, that's how we say it's shifting. So some key properties of the Dirac delta function, Dirac delta function are number one, scaling. We have scaling, so that tells us that the delta of AT is the same thing as 1 over the absolute value of A multiplied by delta of T. And that happens for any non-zero constant A. Okay, we have scaling. Number two, we have shifting. We have shifting. Oh, or should the other thing I said, is it shifting or shifting now? I think it should be shifting. So we have shifting, that is delta of T minus A shifts. It's not shifts. Shift the delta function. Shift the delta function to T equals A. Okay, that's shifting. And then we talk about integral. Integral. So for integral, we have that the integral from minus infinity to infinity of delta t, or delta of t rather, dt is equal to 1, meaning that the integral of the delta function over the entire, so you see, it gives the property of a distribution and probability over the entire real line is equal to 1, which is a key feature, of its impulse, nature. So that goes. So let's talk about Laplace transform. Laplace transform of the Dirac delta function. So the Laplace transform is a mathematical tool used to analyze linear systems, especially in the context of differential equations and control theory. It transforms a time domain function f of t into a complex frequency domain function, big F of s, where the Laplace of f of t as we always know it, is the same thing as big F of S, and that is equal to integral from 0 to infinity of e raised to power minus st f of t dt, as usual. So for the Dirac delta function, the Laplace transform is straightforward. Due to its shifting or shifting property. So the Laplace transform of delta into t minus a, where a is greater than 0, is the Laplace of delta into t minus a. Okay, that is integral from 0 to infinity e raised to power minus st delta into t minus a dt. All right. So by using the shifting property, of the delta function, we evaluate. And I think we talked about that at some point, right? Um, Before we go even to the properties. Okay, yeah, we have this f of a thing going on there. So because of the impulsive nature. So we evaluate the integral, to have the Laplace of delta into t minus a, and that is equal to e raised to power minus sa for s greater than 0. So just like we saw previously, right? If you have an expression like this, so at the end of the day, you just, pick out this function when the value of t is equal to a, basically. So once you see an impulse, once you see a Dirac delta function like this, so just put a for t in this expression, and you're in the kernel. I think that's what we can call the kernel. Just put a for t there, and that's your result easily, If you remember when we looked at the unit step function, right, we'll still have to divide by maybe s or whatever stands beside the unit step function. But in this case, just use replace uh a for t in e raised to power minus st, and you have your result basically. So this result shows that the Laplace transform of a shifted Dirac delta function is a simple exponential term, the simple exponential term e raised to power minus sa, which is a powerful tool for analyzing impulse-like signals in systems So this is analogous. This is analogous to a system responding instantaneously at time t equals a. So let's talk about generalized Laplace transform of the Dirac delta function. Guess I want to switch over now, and then I have this. So generalized Laplace transform of the Dirac delta function. So for completeness, the Laplace transform of the Dirac delta function can be generalized to include shifts and scaling. So we saw those two properties of shifting and scaling previously. So number one, for delta AT, where A is not equal to 0, so the Laplace of delta of AT is simply 1 over absolute value of A, then the Laplace of delta t. And in that case, we just simply have 1 over absolute value of A. Since there's no shifting in this case, there's no shift in the t, right? So we just have this kind of situation. Okay. Thus, the Laplace transform, thus the Laplace transform of delta of AT is 1 over absolute value of A, reflecting the scaling property of the delta function. Okay, that's one. Then two, we say that for delta t minus A, the shift is incorporated. So there's shifting here now. The shift is incorporated as the Laplace of delta into t minus A, and that is e raised to the minus as for A greater than 0. We have this. So, this, yeah, we have as like that there, just taking the place of t. So this result shows that a Dirac delta function that is shifted, by A in the time domain, corresponds to a simple exponential So a simple exponential. So a simple exponential, right? In the Laplace domain, the Laplace domain shifted by A. All right. So let's talk about an example. So um so consider the following first order differential equation with an impulse input and this is the equation. We have dx of t dt plus x of t, and that is, so we have an external force in which is impulsive, and with initial condition x of 0 equals 0. Okay, so this is where the impulse comes in. The goal is to solve the differential equation, solve the differential equation where delta of t minus 2 represents an impulse at time equals 2. Okay, so we go for step 1. So we take the Laplace transform of the differential equation. So that's what we have to do there. So I'll just go straight for that. So we have the Laplace of dx of t dt, k, plus the Laplace of x of t, and that is equal to the Laplace of delta of t minus 2. Okay, so if we do this, for this now, we just know Laplace of x of t dt, as we know already, this is going to be s multiplied by x of s minus x of 0, the initial condition. So for this now, this is what we have. Then plus the Laplace of x of t is simply x of s, basically. And then when we come to the impulse side of things, that's just what we did now. This is simply going to be e raised power minus 2s. Okay, so this now is this, and then for this we have this. Okay, so all that. So with this in place now, we know that the initial condition x of 0 is 0 easily. So we just have s, x, s, small s, right? Small s multiplied by xs minus 0, because this is 0, plus xs equals e raised to minus 2s. So we have sxs plus xs equals e raised to minus 2s. So that's what we have now. So we can solve for x of s. So we can solve for x of s. So we can just have xs into s plus 1. X of s comes out here, and if you factor it out here, it remains only 1. So by the time you expand this, you get this back, right? So you have xs into s plus 1 equals e raised to minus 2s. And since we are looking for xs when we solve that equation, so xs is simply e raised to power minus 2s all over s plus 1. Okay, so this is our xs based on what we have now. So next thing is to take the inverse Laplace transform since we are solving that equation. So we have taken it into the Laplace domain, the complex S domain. So we can go back to step 3. We can go to step 3 where we get it back in time domain by taking inverse. So step 3, take the inverse Laplace transform. So now we take the inverse Laplace transform of x of s. So we have we have inverse Laplace of x of s, and that is equal to the inverse Laplace of e raised to power minus 2s all over s plus 1. Okay, and whenever we have this, um, so with what we actually have here, right? Um, Okay, so I think we need to do this carefully. So the inverse Laplace of x of s is simply x of t on the left hand side, but here we need to handle this carefully. Um, okay, yeah, okay. Let's do it this way. Okay, let's do it this way. Let me try to give some breakdown before we do what we have to do. So generally, first of all, we know that the inverse Laplace of 1 over s plus 1 generally is e raised to power minus t established. We know that. Then we also know, with that in place, right? Since we have it together with that impulsive expression, so that impulse is automatically going to affect this e raised to power minus t by the time we put the two together. So that at the end of the day, by the time we take the inverse Laplace of that, so the inverse Laplace of x of s, of course, we know this now will now be x of t here, and that is equal to so because of this one being together here now, so instead of s plus 1 now we are going to have this 2 now tells us we have shift 2 a shift of 2 in the time domain. So this will now be e raised power, instead of e raised power minus t, we now have e raised power minus t. Normally it should be minus t, um, oh, just minus t, but now we have a shift of 2, so that we now have u into t minus 2, basically. So that's like the result now. So where u of t minus 2 is the unit step function or Heaviside function, okay, defined as u of t minus 2, 0 at t less than 2, and 1 at t greater than or equal to 2. So you see, we started with Dirac delta, and we end up with Heaviside. So it means there's a connection between the two. So what can we say? Say thus the solution, to the differential equation, the differential equation, the solution to the differential equation, the x of t, the t plus x of t equals delta t minus 2 with initial condition x of 0 equals 0, is what we just got now, is simply x of t equals e raised to power minus t minus 2 u of t minus 2. That's the solution right there, which represents a delayed exponential response, a delayed exponential response starting at t equals 2 caused by the impulse, at t equals 2. So this reflects the fact that the system responds instantly to the impulse at t equals 2, and the response decays exponentially for t greater than or equal to 2. All right. So can we take summary of key points now? Summary of key points. Number one, the Dirac delta function. The Dirac delta function is a the Dirac delta function is a distribution, that models an instantaneous impulse, Okay, it's more like, um, maybe everything is fine and all of a sudden there's an explosion, something like that. That's a kind of impulse. So then the Laplace transform of the Dirac delta function, delta t minus a, is e raised to minus as, which shifts the impulse, in the Laplace domain. And number three, the Laplace transform of the delta function is a powerful tool in solving differential equations involving impulse inputs. Okay, so that goes. Let's move on to, let's take some practice questions. Practice 1, find the Laplace transform of f of t equals 3 delta into t minus 4 plus 2 delta into t minus 1. Okay. Number two, solve dy of t dt plus 2y of t equals delta t minus 3 for y of 0 equals 0. Okay, that's a differential equation there. 3 3 solve is the second order one now. So d squared x of t, the t squared plus 4x of t plus 4x of t equals delta into t minus 5. Delta into t minus 5. Ooh. Delta into t minus 5. Perfectionism at work here. T minus 5. Okay. With the initial conditions, x of 0 equals 0. The x of 0, the t equals 0. Okay. So solve for x of t for sure. Number 4. Number 4. Evaluate. Evaluate integral from 0 to infinity. E raised to power minus t delta t minus 2 dt. So evaluate that. The answer will be pretty simple, as I can imagine. What else? Okay, yeah, let's keep going. Number 5. Number 5, find the Laplace transform. Find the Laplace transform of f of t equals delta into 2t minus 6. Then number 6, finally, solve for x of t, and you have the squared x of t, the t squared plus 5x. Is this not all we've considered? Okay, yeah, I think it's different. Plus 5x of t equals delta into t minus 2. So x of 0 is 0, and the x of 0, the t, is also 0. All right, so let me see the answers in the comment section, either on Facebook or on YouTube. Let me also say in the comment section if you have, let me know in the comments how helpful these videos are for you. And if you'd like me to teach a topic or solve a problem, I may be able to find time to deal with all of that. And if you have subscribed to this channel, thank you so much. And if you haven't, please go ahead and subscribe. And for everybody, don't forget to hit the notification bell so you can always get alerted each time a new video is released. And be sure to like and share so that more people can have access to this great content we have on this channel. There's a lot to learn in almost every area, every aspect of mathematics, and even scientific computing with Python. Till I come your way again, keep doing maths right. Bye.